Okay, this is going to be the last half of section 6.2, what we didn't finish yesterday, and also an extension worksheet. You should have that if you're listening to this video. Let's see. What were we saying? Example 9, is that the last one? Example 9 we didn't do yet?
Yeah.
All right, so example 9 says to evaluate. Remember we did, just before we left yesterday, I said if you're doing a definite integral, that you have to u the limits of integration if you want to find the answer to the question using u's instead of x's.
Yes, I do remember.
Does that ring a bell at all?
That
That's what we're going to use here. So it's the integral
Oh yeah.
of x over, is it x over? X squared minus 4. Okay, based on any experience you've encountered so far, what do you suppose we ought to let u equal? Good idea. Why?
Because it's underneath.
Because its derivative is something like this. And it's underneath.
Yeah.
Okay.
So it's just
We'll let u equal x squared minus 4, then du will be
2x.
2x dx. And I don't have a 2x dx. I have an x dx, so I want to do one more step.
Take out 2 1/2 du.
So now I can clearly see that x dx is going to get replaced with half of a du. So it looks like this now in the rewrite. 1/2 integral. My du is at the end here, and I'm going to have a u down here and du up here.
Why'd you So that turns into the natural log.
Yeah, it will be. It will be in a minute. But notice I did not put the limits of integration here because they're the wrong limits.
We have to.
We have to
Well,
u them.
the x in the numerator.
We replaced
It is x dx got replaced with du and a 1/2.
And I was like, oh. Okay.
No, it's what the constant.
Now, if you don't like that, Connor, if this doesn't look right to you, then you can do this. That's just fine. Either way.
That seems like log natural. Well, I don't know.
Yeah.
Does everybody follow that? Okay. So then, I didn't put limits of integration here on purpose, and I'm going to do it the way that I taught you second yesterday. I don't want to integrate this and bring the x back and then use those limits. I want to stay with my u's, but I want new limits of integration, and to find those, you have to u these. So u of 0 is what?
-4.
-4. And u of 1 is?
-3.
-3. So I'm going to integrate from -4 to -3
Whoa.
and stick with the u's. Does that make any sense to you?
Wait. Yeah. Yes. Wait. 1 second. Oh, this was that second one we did yesterday.
Right, and I'm
Okay.
using that method. So I'm going to stay with the u's now. I'm not coming back to the x's because I've already adjusted everything. Everybody clear? So now what I have is the antiderivative of this is what? Natural log of?
U. You need to do that. You don't need to do that, do you?
ln what?
U. Absolute value. Because you can't log negative scar.
You're going to see why that's exclusive. Very, very important. If I did not put absolute values on there and I plugged these in, I wouldn't be able to log them. Very important that you remember that when you have a log, it's the absolute value. Okay? And I got a 1/2 out here. Evaluate it from -4 to -3. Yeah? Everybody clear? And I'm never coming back to the x's because I've already made the adjustment. This is really important because as soon as you go to plug these in, you'll realize the importance because you can't log a negative. So what I get is 1/2 parenthesis natural log of -3. I'm sorry, absolute value of -3 minus the natural log of the absolute value of -4. Which, if you remember your logs at all, is 1/2 the natural log of 3/4.
Wait, how do you do that?
Yeah, I don't remember my logs.
Oh, wait, yeah, you can like do the minus.
Oh yeah, it's because of the order.
Differences of logs end up being the log of a quotient.
Whoa. That's cool.
And that is a number. It's just plain old, I don't know what it is, but it's just a plain old number. It's a negative number because the log of 3/4 is negative. So the area under this curve from 0 to 1 is a 1/2 log 3/4. Interesting.
Kind of.
Did you follow all that and remember a little bit about logs?
Yeah.
Yes.
So To get the u of 0 and 1, we just plugged in those into the function.
You replace the
for u.
x's with those individually into u so that you can find out what the u values are when x is this.
Okay.
So you understand that?
Yeah.
We have to u them. So we get the new limits of integration. Then we can just stick with u. We don't have to come back to x after we integrate. You could, but you need to know both methods. This is used much more often. Because generally, plugging it in is way easier than anti-deriving, coming back to the x's and then plugging those in. There's more to it. But both methods work. It's just that the way the instructions are phrased on your final exam, if you don't do it this way, you won't get full credit. So you need to know this method. It's usually better anyway. Are we okay, everybody? Now listen, I have a little star by my finally that the author offers you. So I'm going to read that to you. It's just before the quick review on page 337. Big old long paragraph. Just give you some context. Finally, consider this historical note. It's not. The technique of U substitution derived its importance from the fact that it was a powerful tool for antidifferentiation by hand. Antidifferentiation derived its importance from the fundamental theorem, which established it as a way to evaluate definite integrals, values under strange curves. Definite integrals derived their importance from the real-world applications people learn to do. While the applications are no less important today, the fact that the definite integrals can be easily evaluated by technology has made the world less reliant on antidifferentiation procedures, and hence less reliant on U substitution. Consequently, you have seen in this book only a sampling of the substitution tricks that calculus students would have routinely studied in math. Case in point. You may see more of them in a differential equations course, which if any of you are headed towards engineering, will be taking. Many differential equations courses.
They're fun, actually.
They're fun. They're good. You'll like them, and you'll be ready for them. Okay? All right. The main thing here is it says, while the applications are no less important, the fact that the definite intervals can easily be evaluated by technology, consequently, the fact that we can do it on a calculator, we're less reliant on U substitution. Consequently, you have seen in this book only a sampling, which is why you get an extension after we handle some of your questions. I've given you an extension worksheet. It's not in the book because he didn't follow through on all the U substitution.
You gave us an extension worksheet?
I will in a minute.
Oh.
I want to know if you got any questions first before I go.
Yep. No, I just wanted 30 to start. This is the first one.
So you did number 21, okay?
I was able to follow it in the book, yeah.
Oh, I want to do number 21 in a minute. I'll take care of yours first, but 21's a great lead-in to what we're going to do next. So if you've got a question about 21, hang on, I will get to it. You said 30?
Yep.
Number 30 says 3 sine to the negative 2. That means 1 over sine squared, which is cosine squared. And we have someone whose derivative is cosine squared version.
That's how they got it.
Okay. Can you run with that?
I think so.
It's an identity first.
Yeah.
Is that enough to get you going?
I think so.
All right. If not, if you get hung up, let me know. But that's it. Get you started. Anyone else?
I think I was able to do 33. I did circle this one. I'm pretty sure I was able to do that. Yeah, I was not able to do 33. That's what I was.
Okay. So let's do number 33. Where we have the 6th power of the log over x.
Yeah.
When you see this, you're going to go.
I usually do.
It's okay. It's all right. It looks weird. Log to the 6th of x over x. How much board space I have left? Maybe over here. I'm going to come over here. You can see it well enough, right?
Yeah.
Okay. So is it a definite integral or an indefinite?
You can see it definitely.
Natural log, 6th power of the natural log of x over x dx.
Yeah.
Okay. Now remember I told you that if you have denominators, it's often good, not every time, but most of the time it's good to let the denominator be u. That's not the case here.
Okay.
We're also not going to let it be the 6th power of log x. We're going to let it be just log x.
Oh.
Can you see what's going to happen now?
Nope.
Okay. What's du?
1 over
1 over
U. 1 over x.
X. dx. Can you see your 1 over x dx right there?
Yeah.
So this turns into the integral of what?
Natural log.
U squared.
U to the
To the sixth.
sixth.
That's what I meant, but. Over.
No, I'm not done yet. U to the sixth
Du.
du. That whole du is the 1 over x dx. See it? You see it all there?
I see.
A little bit hard to reconcile with fractions. Now this is easy to integrate. What is it?
1/7 U to the 7th.
1/7 u to the 7th,
Yes.
which I'm going to replace right now just for the sake of moving on, would be the natural log of to the 7th of x.
Plus C.
Hold on.
Don't forget the C.
Did you catch a con?
Don't forget put it.
I think so.
This is the exception when you don't let the denominator be that, because this numerator's derivative involves the denominator you want. If you're clever, I shouldn't say clever enough, you're a clever guy. All of you are. But if you have done this enough to realize you want to let it be logged so that this can be a derivative rather than log 6.
It's like with the trigonometric ones.
Yeah.
We had the sine cube.
Yeah, sine cube needs to be renamed, and then you rename the sine squared. Anyway, did you follow that? This is one case where you don't let the denominator be because the numerator's derivative involves the denominator. Okay. Any other questions? Anybody? Any snags yet?
No, only on 33, so.
Okay.
I'm only heavily stuck.
Everything else is good?
Yeah.
Okay, then I want to take a look at number 21 with you, because if he followed it in the book, he got there. I got a feeling a lot of you haven't even tried it yet, so you don't know that there's trouble with 21.
Yeah, I followed it in this deal.
There's trouble with 21, and it's a great lead-in to what you have to do on the worksheet. So let's do 21 together so you can see the type of thinking. First of all,
Actually, no, I had to go through an internet walkthrough for that one.
Okay.
Even follow it.
all right,
I had to go to think.
So dumb.
listen to me. Shh. Before we can even discuss number 21, you've got to recall or look up your inverse trig derivatives. Inverse trig derivatives. And reacquaint yourselves with those. They are all 1 over something, involving squares and square roots and absolute values and stuff like that. You remember them? Find them. Find a source that has your inverse trig derivatives.
Okay.
Because if you're not familiar with them, you'll have no idea what I'm doing.
1 plus U squared is tangent. I don't even
Inverse
think.
tangent's derivative is 1 over 1 plus u squared, right?
Yeah.
Sine is
1 over square root of 1 minus U squared.
Yeah.
Are there good ways to remember these?
and secant is
1 over absolute value of U square root of U squared minus
I don't have a way to memorize it.
1. You know.
I don't have a good mnemonic. I don't.
You just memorize it.
Okay, so here is what 21 looks like. It's the integral of dx over x squared plus 9. Now, that's the same thing as 1 over x squared plus 9 times dx, right? And that 1 over x squared plus 9 looks a lot like a derivative that we were just discussing. Goes with tangent, but it isn't quite right, because tangent says it's 1 over x squared plus 1. So think about this with me for just a minute. What we want, if we're going to use inverse tangent for this, what we want to happen is for the denominator to be 9x squared plus 9, so we can factor the 9 out. That's an easy thing. But it doesn't look like that. Can we use a U substitution to force the issue?
What? Yes.
That's, do you understand that this is what we want? That's what we wish we had. Because we can factor the 9 out and have 1 over x squared plus 1, which is the derivative of inverse tangent. You see that? That's what we want.
Yes.
So what we really want is for x squared to be 9u squared. That's what we'd like. We want to be able to replace x squared with 9u squared plus 9. Because if we had 9u squared plus 9, we could factor the 9 out. So write down what you really wish you could have here, which is x squared equals 9u squared. That's what we wish.
That sounds cheap though.
Solve it for you. Solve it for you so you can tell what you want u to be. It's it's x squared over 9 equals u squared. So u is x over 3. That's what we want to let u equal. And that's a hard thing to tell from this. What you do is you write, if only it were this. How could I make that? If I had this, I'd be okay. Or some expression like this. I really need this thing. If I'm doing u, I need this x squared to really be 9u squared. So you write it. Solve it for you. It'll tell you what you want u to be. But you got to do a little work on it. You can't just tell like you have with the other ones. So you got to figure out what you need. Write down what you'd like. Solve it for you, and now we know what u should be. So I'm going to reverse this so that it looks like u. I'm going to reverse this so that I have u equals x over 3. And now I proceed.
It tells us what
It tells us that.
This is how you figure out what you want to let u equal.
No, it tells us.
It tells us u is x over 3.
It does?
Yeah.
Well, it won't in the future.
Okay.
Okay? But this is why they chose x over. I'll tell you that. That's why they chose to let
Now
you
we
let.
know what to
Because
do with
you
it.
may say, why would they do that? This is why. So what is du?
That's painful.
No, it isn't. This is the same thing as 1/3 x.
Over 3.
What's the derivative of 1/3 x?
Over dx.
1/3. Yeah.
We're just down.
Yeah. Don't get too hung up on. Okay.
I was going to do.
Which means that 3 du is equal to dx. So I have this, and I have this, and I want to rewrite that integral in terms of u. So I'm going to have a 3 and a du, that replaced the dx. And here I'm going to have 1 over 9 u squared plus 9. Because u was x over 3. So x squared is, well, let me see if that's right.
So can we just factor out a 1 9?
What's that?
Where'd the 3 go on the 3D?
That's why it's
Out
out
here. 3 du is equal to dx. So dx got replaced with 3 du.
Now we can take out a 1 9.
Hang on a minute. Let's make sure we've got this thing down.
That's right. If you use no, confused on that.
This does not.
X squared got replaced with 9u squared. So that this could happen. And then we got our du correct. The reason we had to have this is so that we could get the du part right. Okay, so far not really. X squared got replaced with 9u squared, which is our first substitution up here. The reason why we had to follow through and solve for u is so that we could get the correct du. That's why. You see what I mean?
Yeah.
But still, x squared gets replaced with 9u squared. Now we factor out the 9, but it comes out in the bottom. So I'm now down to 1/3 because 3 over 9 is 1/3. The integral of 1 over u squared plus 1. Now that's something we recognize and can antiderive. So the answer is 1/3 of the inverse tangent of u. But u was x over 3.
Oh,
Got it.
Crazy, huh?
it's 3 over.
So there were 2 reasons we wanted this. So that we could get the correct du, and also so that we knew what to place in here for u after we inverse tangent. Or antiderive to get inverse tangent. We have to get the correct du so that we can get this correct number out here. See that? It's quite an extensive process. People got really, really good at this after about 20 years after calculus was invented. They knew this stuff. They could do it. Now you get to learn to do it.
This is
No.
just.
Did you follow this or not?
Yeah.
This
Okay.
is crazy.
Now, let me show you. We're going to do the first example on the worksheet together to give you an idea. And then you got to run with the idea and be clever. And it has to do with this very same thing, where it's not clear what we're going to let u equal. But where it is maybe clear what we would like it to be, what things we would like to have. Oh, these are the worksheet, just a minute. I just copied it, but I don't know where I put it.
Right there next to Jake.
Is that the goal?
There's one other thing I need you guys to do. Eventually, I'm going to be videotaping this class as an alternate thing for this stupid award I'm trying to get. I'm kind of wishing I had done it. It's a parent permission to use your image on a video.
Can I just?
This
force
video will
signature
not
from
be
my
sold, it will only be viewed by about 3 people. What?
dad?
Are you 18? Is anyone in here 18? Did you sign your own?
Not even said.
I have the same name as my dad.
I'm
though, so-
almost 18 in September.
Is it the 10th? But you're almost 18?
If you choose to forge it, Mr. Rio, if you choose to forge it, it will still be legally binding. So if you can't say, I never signed that, I say, well, it's signed, so. that's
Say,
all.
I am the youngest that will ever be, and the oldest I will ever be.
Don't you dare.
And we need to get one, so Brooke and Savannah, make sure you get one of these from me, I'm gonna need a signed copy. Okay, enough of that, I just saw it sitting there, I thought I better tell you before I forgot. So here is the extension of use substitution. When people do the first 2 or 3 of these and fight through it, the last couple, it's pretty exciting, it's pretty fun, it's pretty powerful. We're gonna do number 1 together, and then the rest of it becomes an assignment. I will help you with them if you like, but I'm not gonna do them on the board for you. We're doing number 1 to give you an inkling of an idea what to do.
We can work together.
You can. Make sure you learn it though, because you're gonna have to demonstrate that you have a knowledge of it by yourself. So here is the very first one. It is the integral of x over the 4th root of x plus 2.
Well, that's the fourth, right?
That's a 4th root. I know it's a little tiny, but you should be able to see it. Even my eyes can see it. Yeah, it's a 4th root. Pay attention to that. Okay, now I'm going to tell you what to let u equal, so you can see how it proceeds and perhaps give you an idea of what to let u equal in the next one.
Is this one of those things where we know what we would like it to equal, so we're gonna try to force it to do that? Like,
Kind of.
just-
Kind of, sort of. It's a good lead-in. I would like to have the denominator, here's the deal, here's the idea here, at least on the first couple here. I would like the denominator to be a single term, because if you have a monomial single term instead of this 4th root of 2 terms, if you have a single term, you can put it under each of the pieces of the numerator one at a time and do an integral separately on each one. It's always nicer if your denominator can be a single term. Okay?
So can we turn the?
So to make that happen, I probably should let u equal x plus 2. That way I can have u to the 1/4 in the bottom, and that's a single monomial. You understand? So I'm going to let the x plus 2 du is equal to what?
dx.
Just dx. So I'm going to replace dx with du. That was easy. But then, and here's where the extension comes in. Just wait. What in the world is going to replace this? I don't have anything that's just x.
But you have x plus 2.
Yes, you do. So
you minus 2.
this becomes u minus 2 equals x. So we solve this equation for x, and now I've got a replacement for x in terms of u. So the integral becomes u minus 2 over u to the 1/4, which algebraically is easier to handle because you can write it u over u to the 1/4 minus 2 integral 1 over u to the 1/4 du in both cases.
What?
This goes under each of these. That becomes a separate integral because we have 2 different terms. That's the reason why it was desirable to have the denominator be a single thing. You should put it under each of these. And the reason why we ended up with 2 things up here is because of this little maneuver. But it's okay to have several terms in the numerator if you have only one in the denominator. If you can create that situation with u substitution, you should, because you can put this under that one and this one under that one, and then you can use your algebra to simplify each. This is u to the 1, and u minus 1/4 is 3/4.
So if you did 3/4.
So this is the integral of u to the 3/4. Notice I haven't integrated anything. I'm just cleaning things up. Minus 2 times the integral of u to the negative 1/4.
You need du, right?
Why is it a negative 1/4?
Because I brought it upstairs.
Yeah.
So that I can use the power rule to anti-drive.
Oh, so we just use the power rule, so you get
Okay, I get it.
Do the 7/4.
This right from here to here is just algebra. You understand that? So is this. That too was right.
Right there.
Oh, yeah, it's right here. When I put 2 over u to the 1/4, I just brought the 2 constant out so I can have 1 over u to the 1/4. Is that okay? You can leave it inside, but I prefer to let my constants come out. My constants, I let them come out. I sound like I said something else?
Okay.
Yeah, I kinda did. You kinda said like constant to something.
I thought it was.
So that you can come out.
Okay, there we go.
Are we good?
Now.
You understand this so far?
Just like-
Now we have arranged things and got things done so that the antiderivative shouldn't be too hard. What's this going to be in the antiderivative?
4/7 to the 7/4.
7/4 times
4/7.
4/7. Do y'all understand that?
Yes.
Minus 2 times,
The same thing.
No, it's
4/3
4/3.
u to the 3/4.
so this will go up a whole unit, which is to the 3/4, and this has to be the reciprocal to make it a 1. Everybody clear?
Yes.
So what we have is 4/7 x plus 2 to the 7/4 minus 8/3 times x plus 2 to the 3/4 plus c.
Holy.
That, totally unexpected when you start with this, but that is its antiderivative.
That's disgusting.
It is, I agree, but you gotta learn it.
Derive that and put it back into that.
No.
If you derived this, you would get this.
Like, can we do that though?
Sure. If you want.
Oh.
You want?
Yeah, sure. Let's do it.
Okay, I'll come over here.
Okay.
Because I got more room on my tape up over here, so. I have 4/7
I'm just gonna walk through my
x plus 2, 7/4 minus 8/3 x plus 2 to the 3/4 plus c. Okay, so we're gonna derive that. If I derive this term right here, what's the first thing?
We multiply
This
that.
Times this,
Yes.
which is?
Plus 2. Yeah.
1.
Which is 1.
Yeah. So
X plus 2 to the 3/4. Times the derivative of the inside, which is 1, but don't forget that. Minus, what's this times this? 2. Isn't it?
Yeah, it is.
2 times x plus 2 to the
Negative.
-1/4. And the derivative of that?
0.
0. So I have, let's see, we're gonna need I've got my derivative done, so now I've just gotta turn it into that. So this would be x plus 2 to the 3/4 minus 2 over x plus 2 to the 1/4. Do you agree?
Yeah.
The common denominator is x plus 2 to the 1/4. So I have to multiply top and bottom of this times x plus 2 to the 1/4 over x plus 2 to the 1/4. And that gives me x plus 2. Because 1/4 plus 3/4 is 1 when you multiply these guys. So this numerator is x plus 2. This numerator, since it already has the common denominator, is -2. And it's all over x plus 2 to the 1/4, which is x over the 4th root of x plus 2. Voila.
I knew it was gonna happen, but I'm just so
It's so
pleased
impressive.
that it did.
Okay, I'm glad. So totally unexpected, but we've shown that it actually is that.
Nice.
And it all comes to do with, as you said, Connor, what do I want? This is ugly. I would refer that to be one thing. Remember about your algebra. Having one term down here makes it nice for putting it under each and making separate integrals. So how can I make that one term? Let this be u so that I have the 4th root of just one thing.
So when you're doing that, you want to still have some effect with u. You don't want to just take the whole 4th root of x plus 2 and make that u.
Because your derivative of that will never turn out to be some form of x. And it'll be very difficult to solve for x the way we did here.
So you're going to leave some power up there so it becomes x.
I would leave powers in the integral. Okay? So there's your first one. You've got 1, 2, 3, 4, 5 others to do. I would not tackle them until you have done this assignment because it'll give you much more confidence in your
This
use of it. But you wanna get going, because you have the rest of the hour.
Could you do 42?
I'm gonna do 42 on, if you don't need 42 and you're watching this, that's the end of the lecture. We'll do 42.
Oh, it's only at 42. Oh, 42. It says not to do 42.
Yeah, we don't.
Yep, take it back.
You could do 42, it's very, very much like,
They
and I
just
haven't.
bring in like a whole nother variable.
No, it's just like 21. Same idea as 21. You could do 42, and you probably should practice it. If 41 was, or 21 was not enough of an example to have to do it. All right, so I guess that one's out. See you later.
Well, that was timing.
Yeah, good timing.